I've kept up on the board here the work that we did in the last video. So just to remind you, we were trying to look at this function, f of x equals x squared. We were trying to guess the slope of this tangent line to the function at 1, 1. That's the line that captures the behavior of the function just as it passes through that point, so that the slope of the line is going to tell us that it's going up at the same steepness of the curve at that one particular moment. Obviously, since the curve curves, the steepness changes. So I get a different tangent line with a different slope at other locations on that curve. Now, we had created this lovely table of values. We had some points that were a little bit bigger, so to the right of 1, but approaching 1, getting closer and closer to it. And then we had some points that were on the other side. They were smaller than 1, so they were on the left side of 1, but getting bigger and bigger and approaching 1. And we saw that with both parts of this table here, the pattern that we had that the x was going to 1, the slopes of the secant lines seemed to be getting close to 2. So we guessed that the slope of the tangent line, which is also called the derivative of f at 1, we had guessed that that was 2. But a table is never going to allow us to know that for sure. Because while I can be pretty confident that my answer is between 1.999 and 2.001, there are infinitely many numbers in that interval. 2 is just one of them. Also, it's entirely possible, although I'd be kind of surprised if I discovered this at this point in my math career, that my function does something weird or unexpected as it gets closer to 1. This function I'm pretty familiar with, but some functions that I'm less familiar with, I might not know exactly how they behave. So what I want to try to do is improve upon this. Okay. So you may have heard that a picture is worth 1,000 words. That is such an underestimate. A picture is worth an infinitely large table. Because while I can't create a table of values that has infinitely many points on it, so I have to stop somewhere, and that's why a table of values is never good enough, when I draw a picture, I'm drawing infinitely many points. This is infinitely many points on the graph of f of x. I'm going to try to draw a new function whereby y values are, I'm going to call them m of x. And these tables of values here are going to be a table of values for this function. The input x is just going to be the x value of my second point. The output, the m of x value, will be the slope of the secant line that I get. Okay. So I'm going to graph that function over here. It's probably going to look very different from this function because it's not the same as f. But I can use this picture to sort of figure things out. Here's my point of tangency. Now what I'm going to do is I'm going to just label an arbitrary point. So rather than picking a specific number, I'm just calling this point x squared. So that represents an arbitrary point. I do want it to be a point that's different from 1, 1. So I'm supposing that x isn't 1. But notice, I could put a point over here, and I could call that point x squared just as well. So there's nothing in the name that tells me it has to be at a particular location. And then I can draw in the secant line connecting those points. And if m of x, this new function that I'm trying to create, is the slope of the secant line, well, that's just rise over run. But that would be the y value of this point minus the y value of that point. So that's going to be x squared minus 1. Over the run would be x, the x value of this point, minus 1, the x value of that point. Now, I chose to start my subtraction problems at this point. I could have also said 1 minus x squared over 1 minus x. It does not matter, remember, which point you start at. It does matter that you are consistent. And I prefer to let my variables stay positive, or at least not have a negative sign in front of them. So I usually will start with whichever point looks more complicated. All right, so this is a formula for m of x, but I can simplify that formula because the top factors, the top would be x plus 1 times x minus 1. And there's a factor of x minus 1 on the bottom as well. Now I can cancel that. When I cancel, though, I can't just say, oh, that's the same as x plus 1, because I can see I started with a function where 1 was not in the domain of the function. Algebraically, I can see that because 1 would make the denominator 0, and we can't divide by 0. Geometrically, I can see that because this was supposed to be my second point. The first point was 1, 1. I can't choose that for my second point, too. So I need to record that restriction, that x is not 1. That way, this function is m of x. M is a function that will give me the slope of the secant line between 1, 1 and another point. The x value of that other point can't be the x value of that first point. But now I know how to graph that, because I know what x plus 1 looks like. X plus 1, we just have a y-intercept at 1, go up 1 over 1, and connect the dots. Now that's x plus 1. I've actually graphed too much there, because I'm not supposed to have a point when x is 1. So I'm going to have to erase that 1 point. So if x were 1, and I plugged it into x plus 1, that put a point at 2. I wasn't supposed to draw that point. So there's going to be a hole in the graph right there at 1, 2. So m of x is x plus 1 with x not equal to 1. That's my formula, and there's my graph. Kind of cool. Now notice, the y-intercept here is the point 0, 1 we just said. That corresponds to this point here. When 0 is the x value of my second point, the slope of the secant line I would get is 1. If I come over here and I drew in that secant line connecting 0, 0 to 1, 1, yeah, that slope is going to be 1. So these all correspond to points where the x value is the x value of a second point. The y value is the slope I get on this picture over here. Now if I look here, that is not a point. That is a hole. But I know the exact location of the hole. So I'm able to say, hey, look, as x gets arbitrarily close to 1, now I no longer have to stop when I get to be within 1 1,000. I can get arbitrarily close to 1. As x gets arbitrarily close to 1, coming in from either direction, the m of x values are getting arbitrarily close to 2. So we can say as x gets close to 1, m of x gets close to 2, that is the slope of the tangent line. So the y value of a point is the slope of a secant line. The y value of the hole is the slope of the tangent line. Very cool. Now, you saw this arrow notation probably in your pre-calculus classes. The arrow notation is kind of nice because there isn't a point here. So I can't say m of 1 is 2. M of 1 is undefined. But I can describe what the m value, what the slopes of those secant lines get close to. That's proving that this pattern that was suggested by this table of values is actually the correct pattern. Now, we're going to have some notation that goes above and beyond this arrow notation here. I'm going to just write it down. We would say the limit as x approaches 1 of m of x is equal to 2. Now, I haven't formally defined the word limit yet. That's what all of chapter 2 is about. Basically, this equation right here says the same thing that this does. As x gets close to 1, m of x gets close to 2. Okay. And I'll be defining limit a little bit more formally and eventually very formally as we work our way through chapter 2. Right now, this is just a little bit of a preview of the notation that we'll be using in the rest of the chapter as we work our way through this. But this way, we can guess a limit from a table of values. If we're able to get a formula for the function that gives us the slope of the secant line, and that formula is a graph that we know how to graph, and we can see that we get something like this, where we have a known, in this case line, but it could be a curve, but that has just this one hole in it, then we're able to say, hey, as x gets close to this x value, the slopes get close to that unique number, and that would be the derivative.